All right, let's dive into a pretty cool idea. What if our power grid could actually teach itself to be smarter, faster, and most importantly, cheaper? We're going to break down how this kind of self-optimizing system could completely change the game for our most critical infrastructure.
But let's kick things off with a huge question, one that engineers have been wrestling with for a long time. How in the world do you control a system that is in constant flux, where the rules can change in the blink of an eye? And this isn't just some abstract thought experiment. This is a very real problem.
And, when it comes to systems like that, there's probably no better example on the planet than the electric power grid. So let's really get into the scale of what we're talking about here.
I mean, just stop and think about it for a second. The grid is this continent-spanning machine, and it has to perfectly match the amount of electricity being generated with the amount being used every single second of every single day. The balance has to be perfect. If it's off by even a tiny fraction, poof, you get blackouts. It's an incredible engineering feat that we all just take for granted.
Okay, but here's the catch. Keeping that perfect, delicate balance is getting way harder. We're adding all these unpredictable energy sources, like wind and solar. We've got massive new demands, like thousands of electric vehicles all plugging in at random times. And on top of that, power is now zipping between different regions in these huge random surges. The old ways of keeping things under control, they're being pushed to their absolute breaking point.
So, how do you deal with this new level of chaos? Well, the answer starts with changing how we think about control itself. And honestly, the best way to get it is with an analogy. Let's talk about driving a car.
This quote just nails it. The old way of doing things, what we call classical control, is basically like driving a car while only looking in your rearview mirror. You only correct your steering after you've already started drifting into the other lane. But a newer approach, called Model Predictive Control, or MPC, that's like driving while looking ahead, out the windshield. You see the curve on the road coming up, and you act before you need to. So this is the huge takeaway. We're moving from being reactive to being proactive. Classical control looks at what just went wrong. Model predictive control, on the other hand, uses a powerful mathematical model to predict what's about to happen, and then it makes the smartest decision for that predicted future. It's a complete game changer in philosophy.
And this is how it actually works, in this constant, never-ending loop. At every single moment, the controller is peering a little bit into the future. It runs thousands of simulations to find the absolute best move to make right now. Then it makes that one move, and a split second later, it does the whole thing all over again with fresh data. Predict, optimize, act, and repeat, over and over.
Okay, so looking through the windshield keeps you on the road. That's stability. Great. But what if you could do more than just not crash? What if you could also be incredibly efficient about it? That's where this gets really interesting. Let's stick with our driving analogy. It's one thing to just avoid hitting the curb, right? But it's a whole other level to also find the route that saves the most gas and takes the least amount of time, all while dodging traffic jams in real time. That's the next level. And that's precisely the challenge with the power grid. Keeping the lights on is priority number one, no question. That's stability. But running the grid costs a fortune, literally billions of dollars. So the real goal isn't just stability, it's getting that stability at the lowest possible cost. This dual goal actually has a name. It's called economic dispatch. It's this unbelievably complex dance of figuring out, second by second, which power plants to ramp up and which ones to dial down to meet demand in the absolute cheapest way possible, all without, crashing the system. Now, traditionally, this whole thing has been done in two separate steps. First, you've got this high-level computer, the optimization layer, that looks at weather forecasts and fuel costs and calculates the cheapest way to run the grid. Then it sends that target down to a separate control layer, which is what actually operates the equipment. Think of it like a navigator planning the entire trip and then just handing a sheet of directions to the driver. But what if the navigator and the driver were the same person? What if the controller itself could figure out the most economic way to operate on the fly without being told what to do? This is where the real breakthrough is. Because here's the massive flaw with that two-step approach. It's slow. By the time it takes to calculate that perfect economic target and send it down the chain, the real world has already changed. A cloud bank moves over a giant solar farm, a factory suddenly powers down, and that carefully calculated target is now, at best, out of date, and at worst, just plain wrong. And this is the key idea behind what's called
Feedback Optimizing Model Predictive Control, or FOMPC for short. It combines the job of the planner and the driver. So instead of aiming for some pre-calculated target, it's constantly looking at real-time measurements from the grid, like power flow and costs, and it constantly adjusts its own target. It's always asking, based on what's happening right now, how can I be more cost-effective? It finds the economic sweet spot all on its own.
This comparison just makes the difference crystal clear. The old way is this rigid, top-down sequence of events. The new way, FOMPC, is a single, integrated, adaptive loop. It doesn't just control and stabilize. It controls, stabilizes, and optimizes, all at the same time, in one elegant process.
The advantages here are just huge. You don't need to know the perfect target in advance because the controller finds it for you. It's incredibly robust because it's reacting to what's actually happening on the grid, not just what some model predicted would happen. It can handle all sorts of unexpected events because it's always learning and adapting.
So, this all sounds fantastic in theory, right? But what does it actually mean for the real-world power grid? Let's take a look at how this was put to the test. So researchers built this incredibly detailed computer simulation of a power system connecting multiple different regions. And then they just hammered it with exactly the kind of problems a modern grid faces: sudden, unannounced spikes and drops in power demand. It's the digital equivalent of thousands of EVs plugging in at once or a huge wind farm suddenly dropping offline.
And the results? They were pretty remarkable. When it came to the main goal, balancing the grid at the lowest possible cost, the FOMP approach consistently and significantly outperformed traditional methods. Because it was constantly self-optimizing, it found efficiencies that a slower, hierarchical system would have completely missed, and that leads to real cost savings.
So what this really means is this isn't just some academic exercise. For the real world, this technology leads to a grid that can more seamlessly integrate renewables. It means lower energy bills because the system is always hunting for the cheapest operating point. And it means a more reliable, more resilient grid that reacts instantly to problems, all while making sure the actual expensive hardware stays within its safety limits.
This takes us to the big picture. This isn't just about a better way to control the power grid, it's a glimpse into a new way of controlling complex systems of all kinds.
And that's the thought I really want to leave you with. We've just explored a system that can learn to optimize itself in real time, adapting to unpredictable changes without being told what to do. So if we can build a self-optimizing power grid, what other complex systems could we apply this to? From global supply chains to city traffic networks, maybe even biological systems, the possibilities are absolutely fascinating to consider.